Starting now. All right, we'll give it a go here. Give it a go. You can do this. These are easy. I picked hopefully an easy one. We're going to find out. I'll come back for this. Yes, there is a typo. Yeah, there's a typo. It should be the whole thing should be subscripted for that second A. So let me just show. I will do it on here. Thank you for reminding me. Give me a sec here. Where's the scan? Okay, so it'll be there in a sec. What's the problem? Yeah, it's this. This right here. Get rid of that and just call that an minus. Here, I'll write it again. an minus 1 plus 6 an minus 2. Oh, that's also a bad thing. Yeah. There. Here. Let me write it one more time since I blew it. A sub n minus 1 6a minus 2. I don't know why I had to write it again. It looks identical, just in a different color. Yeah, so there, yeah, so use what's on the screen, not what's printed, because the printed thing is, well, not totally wrong, but the subscripts didn't render properly. It's my fault for leaving out a set of curly brackets. Oh, crud. Doesn't factor. What's wrong with me? No, it doesn't. Yeah, here we go. Apparently there's multiple typos. Let me fix. Here. There we go. Let's do this. Sorry. We'll just start fresh and try this as our here, I'll make these negatives here. Now it'll, and now I don't know what's going on over there. I hope that doesn't turn into something ugly. That right there, yeah. -6. Yeah, the -6. Man, I thought I was all prepared for today. I was so excited to get onto graphs. And then this stupid quiz that I just typed up last night. Okay, well. Better to have the mistake on a quiz, not on the test, right? I mean, you could have solved the one. It just would have radicals in it. It would be nasty. Okay. And this should work out with no weird fractions and no radicals. So I did, after all of my typos, at least I got that part right. So. find something? You want me to look at it? Awesome. Yeah, this look good? Is that like the portmanteau of your first and last name? It's fine.
I have no
It's kind of
idea.
cool. No, I love it.
Is that
That
is so funny.
I love it.
That definitely shows how bad I was on Friday. I got to the A, I was like, yeah, okay. Yeah, you got the R.
Yeah, I know you can.
That's so funny.
I've
never seen that before.
I love portmanteaus. This one is pretty
I'm
good.
telling you, it sounds like a band name. You should take it on. I'd go see that before.
I'm not even gonna try to.
Oh, did you create that? That's wild.
I'll just make a check mark at the top.
Wait, did you collect my quiz?
No, I didn't. I was so excited about your new name scheme here.
I never.
Like you could turn that into like a signature, you know, like Hefka. Just whew. And then
That wouldn't even make any sense. Like if I had left off the last A, maybe, and so I was just like, oh yeah, it's more like, you know what I mean, or have to.
all right, well, let's see what I got. I got the same as most of you. There's
Joseph's still not done.
oh, Joseph's not done. I'm sorry, Joseph. No, are you done? No, just put that last number down. You got it. Okay, that last two numbers. You got two numbers? Very nice. So far, so good. Almost there.
Oh yeah.
Well, you can always just, yeah, I got mine did this after, so if you're happy with it. Okay, happy with it so far. And then, you'll see the rest back here in just a sec. All right, here's what I did. Hopefully it's similar to what you did. We get this up here, unfreeze. Wow, it's so big. After finally figuring out my problem with this, there's the characteristic equation. Here are the characteristic roots. They are beautiful, 3 and -2. No fractions, no radicals. And then you go on to say, hey, this is what the general solution is going to be. A sub n is some constant times 3 to the n plus some other constant times -2 to the n. So far, so good. Now we have to plug in the initial conditions. So I've got this one here, which doesn't look good. So I'm going to replace my equal sign. So that's A sub 0. A sub 0 is 1. And when you plug 0 into this, you get C1 times 1 and C2 times 1. And then A sub 1 was 23. And that gave me 1. So 3 to the first is 3. -2 to the first is -2. So that gave me this. And then I used elimination. I multiplied the top one by 3 and then subtracted and got this. And then the answer I got was C2 is equal to -4. And then there was this, it was simply plug that into the first equation to get C1 is equal to 5. So my final answer is right there. So 5 times 3 to the n, -4 times -2 to the n. Beautiful, isn't it? All right, very nice. We do need to move on. So let me find something here fun. Surely this will be more fun. Moving on to graphs. I need to tell a story though of Leonhard Euler, and in particular, so Leonhard Euler, mathematician, he a lot of stuff is named after Euler. You have Euler's formula, Euler's equation, various things that we deal with in mathematics that seems to be attributed to Euler. And so one of the things that he did, though, was he was the father of graph theory, or at least that's some people call him the father of graph theory. You might wonder, how did he start out in graph theory, and where's the there's this possibly apocryphal story that goes along with his his youth, his when he was learning about mathematics. So anyway, he was working in Königsberg, which is now in Prussia. Wait, it's St. Petersburg now. Anyway, Königsberg. And in Königsberg, there are the map of Königsberg looks something like this. This is the city. It's not green space here. There's actual buildings here on either side. But Königsberg is built at the confluence of two rivers. You have River A, I don't remember which river this is, and River B coming in. There's an island right at the confluence, and then the river, the combined rivers flow out of that. Sort of similar to Montreal. If you go to Montreal, it's an island, and there are a couple of rivers around it. But anyway, so Euler at the time, there were 7 main bridges in the city of Königsberg. And so it turned out that Euler was dating a girl, and this girl came to him one day and said, hey, Leonard, you know, all the youth, they do this really fun thing with their time, you know, when they get together, because we don't have Facebook and we don't have like video games that we can play. And so instead of going and playing Pokemon Go or geocaching or whatever it is, what they did was they would try to walk across every one of the 7 bridges on a stroll through the city. And to make things harder on themselves, to make it more interesting, they said, hey, let's see if we can walk across each bridge once and only once. So let's see if we can do that. So here's the city of Königsberg, and let's give it a go. See if you can figure out how you could cross each bridge once and only once. And to help you out, or help us out, I'm going to just label these things. There we go. This is going to be A. This is going to be P. This up here is the North Shore, and this is the South Shore. Just so that when we talk about this, you can say, hey, we're going to start up on the North Shore and then head to the island A. I don't know why I called it A, but it's that island. Or you might say, we're going to start on the North Shore and head to the peninsula, and then I'll know where you want me to go. So take a minute, see if you can figure out, is there a way, and what is it? Because if you have a map, that would make it a lot easier than just wandering the streets.
Do you have to end up on a particular spot?
No, I'm okay if you just end anywhere. Just cross all 7 bridges. That's the goal. Cross all 7 bridges once and only once. And I realized that if you start on the North Shore, you cross them all, and you end up on the South Shore, you'll have to go back home eventually. But I think you would have solved the problem the way that it was posed back then. So I actually had a handout I was going to give you, but sadly, I forgot to print it this morning. It would have had this picture. Instead, I ended up printing this faulty quiz. So does anyone want to give it a go? Or have an idea of, even if you can't do the whole thing, maybe we could get started. Where would you like me to start? Does anyone have an opinion about where we're going to start this journey? Start on the North Shore? Okay, we'll start up here. Okay, here we go. Here are these young lovers walking hand in hand. How do I draw? Is that okay? It's kind of sexist, but oh well. It's back in the 1700s, so it's okay. Okay, so these two, they're going for a walk. So where do they go from the North Shore? Anyone want to? Let's go ahead and do this. Go down? Look, they're just wandering right now. Where should I have them go?
Peninsula.
Peninsula. Hey, great. Okay, so we're here. Yay. Now where?
No, I have no idea.
We have to be south.
We'll go south? Okay, we're going south. Okay, now where? I guess we have to go to the island. Well, no. Look, I think I'm going to do it. Look.
No.
Look. Wait, I'm almost there. Oh. I failed.
Oh, we swim?
No, I'm not allowed to swim.
So to get into by there's 3 bridges. So there's 3 bridges going north.
Yeah. So Joshua's got a good point here. And this is the point that, see, when Leonard Euler was posed this problem by his then girlfriend, he said, "Hold on a sec. I think I can figure this out, and we don't need to walk." And so he went into his study, and he actually generated the basic ideas for graph theory, and then came out and said, "Honey, it's impossible." And she said, "You know what? You're impossible." And she went and started dating a physicist. But anyway, yeah, so he missed the point, of course, is that the point wasn't to cross the 7 bridges. The point was to spend a lot of time with your special friend. Yeah, this is impossible. He figured out it's impossible. And it's basically sort of what Joshua is sort of hinting at here. Joshua, you said there's 3 bridges here, right? Yeah, so think of it this way. If there are 3 bridges on the North Shore, let's just focus on the North Shore there. You're going to have to, if you start there, you're going to have to leave the shore, and then you're going to get back, and then you're going to leave again. But notice that there's also 3 bridges at the peninsula. So you're going to go to the peninsula, leave the peninsula, and then go there again. So you better end at the peninsula. But same thing's true of the South Shore. You can't have this be the case for more than 2 of these. You're gonna have to start somewhere, end somewhere. We're gonna formalize this. For now, though, I want to show you sort of how we get from this picture to graph theory. And we've used graphs already in here, but here's a much worse drawing of the Königsberg situation. And so here's what Euler did, is he said, you know what, we don't really care about the bridges, we don't care about the land masses, we don't care about the map, but what we care about is the relationships. So you have these 4 land masses, and we don't really care that one is bigger than the other, we just care about where they're connected. So here's the picture that we have here. In fact, no, I'll just do it here. We have this picture. And now that he's got the connections, notice that he's got one edge, one line for each of the bridges. So in this case, the land masses are the dots, the nodes, and the bridges are the connections. And so once you have that, we don't need the map anymore. We can just get rid of it. And this is a much easier to digest thing. We're going to be able to deal with this using, well, this graph theory that we're learning about today. So you've done graphs in your elementary discrete math class, and you've, at some point, you did graphs, didn't you? Maybe? Doesn't matter, we're doing graphs. We've done graphs in here before, digraphs. We had directed graphs. Well, we're going to do the formal version of this. So what is a graph? A graph is a bunch of vertices and edges. That's it. You have a bunch of vertices and a bunch of edges. Now, because mathematicians like to write things down in nice sort of formal language, what we're going to say here is that we have the graph is equal to a set that includes the vertices and then the edges. So as an example, graph 1 might be this: A, B, C, along with these edges. I can't remember how we're going to do this. I'm just going to do it this way. How about if too late. I'm stuck. So you have AB, AC, and BC. Those are the edges. So let's go ahead and see if we can draw this graph. So notice that I've got 3 vertices. So put 3 dots somewhere on your paper. I'm not even going to do it up here until you get done with yours. So you've got your 3 dots. Label those 3 dots, A, B, and C. Those are the vertices. Vertices, dots. That's what they are. Once you have those 3 dots labeled A, B, and C, you're going to draw a line connecting each of the pairs listed under the edges. So for example, the edge AB, and then the edge AC, and then finally BC. All right, so we've got something. That didn't take long. Let me do it up here just so that we can compare. I have my vertices, A, B, and C. And you might have drawn yours in a different orientation than mine. Did anyone do them in a straight line? No one did them in a straight line? Okay, you knew what was coming then. But anyway, you might have gone, instead of going clockwise, you might have gone counterclockwise, had the B and the C switched. Fine. Doesn't matter. All that matters are the relationships. In this case, A is connected to B, A is connected to C, and B is connected to C. So when you get done, you should have something that looks like this, some sort of a triangle. And it might, I mean, if you put all the line here, you could do this, A, B, and C. These two graphs are equal. They're the same graph. So if you have two graphs, even though they look different, as long as they have the same information, they convey the same ideas, they're the same graph. Now, before we get into more graphs and more stuff about equality, I need to mention trees, because this is a word. I know you've probably studied trees already, but let me just mention that this is one, it's a graph with no cycles. Okay, just as an example here, let's say that here we go. Graph 2, we'll call this, is going to be the set of vertices is A, B, C, and D. And then the set of edges will be A, B, A, C, A, D. And that's it. So here's A, B, C, D. There's my 4 dots. And then the edges are these 3. Notice that there's no cycles, no loops, if you will. That's a tree. Yeah?
Is this going to be like tied somewhat into like non-cyclic permutations?
You want to relate, I'm sure that there is a relationship between graphs, trees, and permutation groups. But let us not go that far yet.
Okay.
So let's get the basics of graph theory first. So I know some of this is super basic. Some of you are like, wait a minute, I've been dealing with trees all my life. But it's fine. So the reason why these are called trees, if you take this thing and you turn it upside down, it would look something more like a bush, I guess. But there it is. Now that looks like a little tree, A, B, C, D. Certainly if we put maybe if we put another vertex down here, now it looks a little bit more like a tree, but now it's not graph 2. Okay, well, we're going to be interested, what we're interested, at least for graph theory for now, is what's called isomorphisms or isomorphic graphs. So I just need to make a quick note about the difference between two graphs being equal and two graphs being isomorphic. So equal means that the two graphs are exactly the same graph. So for example, these two graphs so those two graphs are the same exact graph. They're the same graph. They have the same labels, they have the same connections. Everything is exactly the same. Like if you were to write down A, B, C, A, B, A, C, B, C. That's going to be the same for both of these graphs, G1, G2. It's exactly the same notation. So that's what's meant by equal. They're equal to one another. They're identical. Isomorphic, on the other hand, means that they look the same, but they're not the same. Okay, I know that's kind of, let me try to explain. So you've probably some of you have dealt with isomorphisms in other classes. So let's deal with it in the context of graphs. So let me make a new graph. How about this? We'll call this G3 and I'll make it red. And let's see, X, Y, and Z. How's that? So G3, not the same as G1 and G2. And the reason is, and I know that you might say that, well, it's kind of picky of you, that looks the same. Indeed it does. but that's part of this is that this is the simplest, well, not the simplest, but one of the simplest versions of isomorphic graphs that I could draw. I'll draw a more complicated one momentarily, but G3 is this XYZ, XY, XZ, and YZ. Okay, so here's the big difference between equal and isomorphic. Equal means they're identical, basically the same thing. Isomorphic means that you can find a function. I can find a function that takes G, well, in this case, it's going to map G3 onto G1 that preserves the edges. Okay, what does that mean? Well, I'm going to have to, have I run out of room? I kind of have. I think I can write it at the very bottom here. We're going to see. And if we can't, I can always go to Notability. Okay, so here is my function that I'm referring to. I'll leave it blue. Okay, so in my function is going to be that x gets mapped to A, y gets mapped to B, and z gets mapped to C. So that's the function there. I know that my notation is atrocious, but I wanted to put it on a line. In other words, this is the mapping. There, there, and there. So here's what I mean by preserving the edges. So now that I've got the mapping, I say, okay, X is just a stand-in or a proxy for A, and Y is a stand-in for B, and Z is a stand-in for C. Once I've done that, let's double check to see if all of the edges down here are represented up there. That's the key. So let's see. So let's check to see, is this an isomorphism? Well, let's do F of XY. So let's do that edge, put that edge into the function F. Well, that's going to map X to A and Y to B. And look at that, that's up there. So that one's good. What about F of XZ? And I know this seems super babyish, doesn't it? I'll get a more complicated one in a minute, don't worry. Okay, so for F of XZ, you have X maps to A, Z maps to C, and so that's this one. So sure enough, those work out. And then one more, F of YZ is BC. Whoops. So that one works out. So that's what it means to preserve the edges. The edges are still there. They're the same edges. Let me just show you an example of a not, here I'm going to have to go back to Notability. Is this here? That'll work. Okay, so here's an example of two graphs that are isomorphic. Let's do this, and then here I'll do this A, B, C, D, E. And here's another one, give me a sec. A, B, C, D, E. Okay. Okay, there's graph 1, and then here's graph 2. Oh no, I erased. Hold on a sec, that's better. So graph 2, give me a sec. Hold on a minute. I messed up. That's it. That's better. So graph 1 and graph 2. So your job, if you want to show that these isomorphic, question mark, is to figure out a function. So maybe I could do it this way. Here, I'll just make my function here. Here's G1, here's G2, A, B, C, D, E. So what can I map what to make this function correct? And then we'll talk about sort of strategies. This one's a little bit, well, quite a bit more complicated than the other one. Because is it, well, first of all, can anyone see that those two are isomorphic just by looking at them? You can tell that they are? Or you can't? But someone said yes? Who said yes? You did? Okay, yeah, outing the other person, that's fine. So what makes you say that they're isomorphic, John?
So both of them, there's one point that has 3 lines. I guess there's 2 points that have 3 lines. There's 2 points that have 3 lines going from them, and then there's
Okay, interesting. So we're relying on what's called the degrees of the vertices. So they're getting a little bit ahead on my PowerPoint, but we're not going to finish the PowerPoint anyway in the next 3 minutes. So let's just mention this, that the degree is number of edges meeting at the vertex. So the degree of B happens to be 3, the degree of D happens to be 3, and the degree of the other stuff are all 2. And so it seems like we should be able to, just getting ahead to my, so I get the exact same is what we're going to go over in PowerPoint, that what we should be able to do, at least according to John, is maybe compare the degrees of the 2 graphs. So let me write this down. This is called a degree sequence. Is just a list of all of the degrees in a graph. So in this case, graph 1, the degree sequence is 3, 3, 2, 2, 2. And in graph 2, the degree sequence is 3, 3, 2, 2, 2. So that's a hint that they're probably going to be, well, they could be isomorphic. So let me say it this way, is if these don't match, if the degree sequences are different, like if this was 3, 3, 2, 1, 1, and that was 3, 3, 2, 2, 2, guaranteed you cannot make a mapping that will preserve the edges because the edges are different right from the get-go in terms of what's connected. However, if you have 2 graphs that have the same degree sequence, it's not guaranteed. You're not guaranteed that they're going to be isomorphic. So I'll have to show some examples next time, but let's deal with this one. These are isomorphic though, that's a good hint. Any other people can visualize that these are isomorphic? One way to think of this is if we could somehow rearrange the graphs. Yeah?
So if you took the triangle ADB and inverted it.
Wait, AD what?
A, D, and B. Like the D point and inverted it.
Oh, move the D up?
Yeah.
Okay, yeah. ADB. Oh, interesting. You're talking about with graph 2. Sorry, I was looking at graph 1.
If you untangle it.
Yeah. So this is what I mean by this whole thing is finding a way to sort of untangle things. And in fact, maybe if we rearranged, so let's see if we can untangle this. Anyway. Here, I won't do it on pen. So here, imagine this. Take this C and just pull it up here so that triangle is up here. That sort of untangles a lot. So now the C is up here, creating a triangle. And then take the B and the D, swap places. And you'll have basically this same shape. You'll have a pentagon with a triangle chunked out in the middle. Anyway, the next step is going to find the isomorphism. So when you look online at the homework, actually I can change it now. Do I want to change it? I don't know. It's not that hard, but I better. Otherwise, you'll go bonkers. So let me look at it. Yeah. Here I do need to say this. Let me pull this over. I got a little sick of our book, and I feel like I need a little mini break. Just a mini break. Not going to be too long. And so I found an open textbook that's pretty good. So that's this one. So you just have to go to this. Yeah, that's not going to work, is it? Yeah, anyway, go to that, and then I'm going to adjust this slightly, so it's not going to be 2, 3, 5, 7, 8, 9. But here, just a minute. Let me try one more time to go to this link all the way over. That's better. So let's copy, open in new window. There we go. Okay, so here it is. And if we go to the end of this thing, you'll find a bunch of exercises. There's lots of explanation. And I'm going to make a quick adjustment to this so that we at least have a few things that we can do for next time. Maybe the first 3. So I'll shorten this a little bit. All right, so and so we're taking a little mini break from Grimaldi because, like I said, I've gotten a little bit discouraged by him. So have a different type sets of pictures to look at.